Welcome to This Explainer. Today, we're taking a fresh look at the circle. We're going to explore it not just as some simple shape on a page, but as this amazing, totally interconnected playground of mathematical rules. So let's just dive right in. Here's our roadmap for today. We'll start with the anatomy of a circle, move into slices and segments, uncover the rules of chords, tackle the 3 points, 1 circle concept, and wrap up with arcs and angles.
All right, Section 1, Anatomy of a Circle.
Think about a bicycle wheel cruising down the street, or the hand sweeping across a wall clock. What's genuinely fascinating about these everyday objects is that their shapes are perfectly defined by one single, unchanging rule, maintaining a fixed distance from a center point. Like, think about it. Every single spoke on that bike wheel is doing the exact same mathematical job, keeping the rim perfectly stable as you ride. It's literally geometry in motion.
And that brings us to the formal definition. A circle is basically a closed curve obtained by joining all the points in a plane that sit at the exact same fixed distance, which we call the radius, from a fixed center point. Pretty simple, right? Now notice the line labeled chord. A chord just joins any two random points right on the circumference. And if you take that chord and draw it straight through the very center, boom, you get the diameter, which is exactly twice the radius. It's the longest chord you could possibly draw.
Moving right along, Section 2, Slices and Segments.
Okay, so this brilliantly clears up two terms that are so easy to confuse: segment and sector. Take a look at the segment first. A segment is basically a chunk of the circle bounded by a straight chord and a curved arc. Now contrast that with a sector. A sector is bounded by two radii and an arc. It looks exactly like a slice of pizza, cut right from the center. So, quick trick to remember. A segment uses a chord across the edge, while a sector uses radii from the middle.
Let's step it up a notch. Section 3, the rules of chords.
Now we're getting into the hidden laws, starting with Theorem 22. Notice the line extending straight down from the center point O, cutting into the chord AB. This theorem states that a straight line drawn from the center of a circle to bisect a chord, meaning it cuts it perfectly down the middle, creates right angles. It doesn't just casually divide the line. It mathematically forces a perfect, flawless 90-degree intersection every single time. There's literally no wiggle room here.
But, let's break down how we actually know this is true, rather than just taking a textbook's word for it. Step 1. We draw that bisecting line from the center. Step 2. We draw two radii connecting the center to the ends of our chord, which suddenly gives us two triangles. Step 3 is where it all clicks. Because both radii are equal, the two halves of the chord are equal, and they share that middle line. Well, these two triangles are exactly congruent. It's the side-side-side rule. Because they're literal identical twins, those angles in the middle have to match. And since they sit on a straight line adding up to 180 degrees, they absolutely must be 90 degrees each. We just proved an immutable law of nature right before our eyes.
Phew! Okay, let's take a quick mental breather and summarize what we've just unpacked. These are the golden rules of chords. First, perpendiculars from the center always bisect chords. Second, the bigger a chord gets, the closer it pushes toward the center. And third, equal chords are always perfectly equidistant from that center point. Lock these foundational laws in your mind, for sure, because they are the keys to unlocking the rest of the circle's secrets.
Ready for more? Section 4, 3 points, 1 circle.
So here's a really intriguing question for you to ponder. Imagine 3 random dots scattered on a piece of blank paper, as long as they aren't lined up in a perfectly straight row. How many different circles do you think could be drawn that pass perfectly through all 3 of those exact points? Go ahead, sketch it out in your mind for just a second. And here's the striking answer, laid out in Theorem 26. There is one and only one circle, which can pass through 3 given points, not in a straight line. What's so wild about this theorem is how it actually works. If you connect the points to form 2 lines, and then drop perpendicular bisectors cutting through those lines, they will always cross at exactly one spot. That intersection, that is your guaranteed perfect center point. And from that specific center, only one circle is mathematically possible. It's like a giant puzzle locking perfectly into place. And finally, Section 5, Arcs and Angles. Check out the beautiful symmetry we've got going on here. The rule is super simple but honestly profound. Equal arcs cut equal chords, and equal chords cut equal arcs. So the big takeaway is, if you take 2 chords of the exact same length and place them anywhere inside that circle, they will rigidly carve out the exact same arc lengths along the outer edge. They are permanently locked in proportion. Now let's step up to Theorem 27 and see how this builds. This rule states that if two arcs of the same circle subtend equal angles at the center, then the arcs are equal. What this means in plain English? It means the angle you create right at the very center of the circle is the ultimate boss. It directly dictates the exact size of the arc on the outer edge. So equal center angles guarantee equal outer arcs every single time, no exceptions.
And, these same laws totally dictate what happens to other shapes when they get trapped inside our circle. An n-sided regular polygon inscribed in a circle subtends an angle of 360 divided by n at the center. So if you drop a perfectly regular octagon, which of course has 8 sides, into a circle, you just divide 360 by 8. It will predictably and perfectly carve that center into neat 45-degree slices. The geometry is just flawlessly consistent.
We've really seen how lines, angles, and arcs obey some incredibly strict mathematical laws today. They aren't just arbitrary shapes, they're this perfectly balanced system of rules operating entirely behind the scenes. So next time you look at a bicycle wheel, a pizza pie, or even just the hands of a clock, ask yourself, what other hidden geometry is secretly holding our world together? Keep questioning, keep learning, and thanks so much for joining me on this explainer.